Thank you for having me at stackconf 2021. In this presentation, I will introduce you the concept of data-driven security, where machine learning, powered by humans, is helping to prevent cybersecurity attacks. My name is Peter Elmer. I'm working as a security expert at Checkpoint Software Technologies, and I'm part of the team of the CTO. So today, we look at the need for data-driven security, the methods that are using, and the value of machine learning powered by human experience. And we look at the effectiveness of these solutions. Short word. Important it is to collaborate, to share experience, and to centralize the intelligence, to distribute then the intelligence, to update, and to make sure that the experience of all members of the team are confluencing into the project, into the team effort, into what you are doing on a day-to-day basis. A sentence from our data scientist team is that important decision points are taken by machines with logic created from data. The logic created from data and machine learning, kind of complicated things, and I try to get an easy entry here. And I talk about something that I like, that is close to my heart, and this is apples. Why apples? Because in the area of Frankfurt, apples are very important. Because you can make two things, apple pie, and you can make apple wine, so cider. So if we apply this concept to machine learning, let's look at it. We have features and labels. So the feature is the result that we want to achieve. We want to achieve, on the one side, an apple pie, on the other side, we want to achieve apple wine. So we need to decide, we need to know which are the features that make an apple good to be used in an apple pie, and which are the features that are more good to become apple wine. So there are features we can touch, we can look at, we can smell, and there are features that we use, we experience, but then unfortunately, it makes something different. It changes the data. So we have features where data remains, and we have features where data is getting destroyed. And the difference between applied machine learning in one way or in the other way is the human experiences that is driving the selection of features. Which characteristics are we assigning for predicting a result, for predicting the machine learning result, the label. And this is the human experience which is making the difference. So in our side, we have 27 years of experience in cybersecurity. We have an enormous amount of data, labeled data, that we know the result in our database. And this is what we are using when we apply the machine learning to prevent security attacks. But I use the word predicting, and predicting is, when we work in technology, always something, well, we didn't want to predict, we want to know. It must be clear, 100% clear. Unfortunately, machine learning always goes along with a little bit of predicting. So if we compare it with the traditional way of programming, even if we be honest to ourselves, there is something quite a little bit characteristics, conceptions, assumptions when we create a program. We create a program on our best intentions, with the best assumptions, with what we know, context, and then we create the logic, and then we feed data into the logic, and we get always a deterministic result. So in machine learning, things are different. In machine learning, we have a machine learning algorithm. We give data to this algorithm, and we know the result, how the data needs to look like at the end. And then the machine learning algorithm is giving us the logic to treat the data, to handle the data. Then we are using new data where we don't know the result, and then the program, the logic, the machine learning logic is giving us a probabilistic result. A result with a good probabilistic to be as we expect it to be. But do we like probabilistic results? So we would like to drive everything from probabilistic to be deterministic. How can we achieve this? We can achieve it by understanding what is making something different, what is changing something to be there and to be then on the other side, or to change its characteristics. And we know that the more data we have, the more data we feed into the logic, this will increase the accuracy. So the more data we have, then more we have the ability to become from probabilistic to deterministic. But we have limited resources. So this is a fact we need to accept. We can't change it because it is limited. Everything is limited. And on the other side, in cybersecurity, we see that the attack surface is always increasing. Now, since more than a year, many of us work from home. We work with multiple devices. We access multiple services, some hosted in a data center, some hosted in a cloud, some consumed as a function, temporary, existing, and all this is increasing the attack surface. And as we read every day in the press, unfortunately, even in many cases, very successfully for the attackers, unsuccessful and bad for us as we are on the other side. So we need to accept that it is unfortunately easier to attack than to defend. It's not really hard to go out to the darknet or even on Google to find attack tools, to find methodologies that you can reuse, or you can even find someone who is doing it for you. There are attackers for rent, hackers for rent. As long as you pay, they give you a result that you would like to achieve. So attackers have an intent, then they have an idea, they have a plan, they design a logic, they create source code, they compile it, and then a stream of bits is sent against the victim. So this is the process. And the surface at the end of the process is huge, a stream of bits, really a complex thing to be dealt with. So what if we would the effort of defending reduce? What if we could capture the intent of the attacker? That would be a cool thing to be achieved. Understanding the intent instead of understanding that this is an attack by looking at the stream of bits, by working on all the huge attack surface. How can we achieve that? Understanding the intent, complicated. Well, and we need to respect that we need to optimize our resources because they are limited. Fortunately, what we found out in our research is that when we apply machine learning, we take 8 times less resources than for example, preparing the data, decompiling an executable file, breaking apart a complicated Office document to understand if there are macro elements, and if there are macro elements, to understand their consistency, what they are doing. So we know from experience that when we apply machine learning, we are more efficient. We can achieve more with less resources. This is why data-driven security is such an important area in the research. And if we apply a mathematical representation, everything becomes really easy. Not really for me, I'm not a mathematician, but my wife is a mathematician, she helps a doctor, our data scientists colleagues in the team are all mathematicians, so I can work with them, trust them, and then we achieve and the team a result. Because they found mathematical representations and they found methodologies to abstract the complexity they see in attack schemes. So how can we understand this? What we are doing is we change representation. And by changing representation, we can look at the example of a VGG16 Convolutional Network element. So the VGG16 can transform an image into a vector, into a stream of numbers. And there are now models existing that allow to predict pictures with an accuracy of 92.7%. So if we feed enough data into a machine learning model, we can achieve to create a logic that is with 92% accurate. And one of the latest applications for this, I just seen it in a paper from Intel, where this technology is applied in enhancing the image quality of a game. So on the left side, you see the original, and on the right side, you see the enhanced animation. And what the team did at Intel, they feeded 5,000 photos from the Cityscapes dataset into a VGG16 model and combined it with the information created by the game. And this is achieving a very realistic, photorealistic experience. I recommend you to search for this article. There is a very nice video created by the team which gives a good introduction into this technology, and it's presenting in a very nice way the result that they achieved. Another example is vectorizing. So vectorizing human language, something that we are kind of using every day. Every day we are using our text-to-speech, speech-to-text functionalities on our mobile devices, on our computers. So what is behind it? If we look at words like king and queen or man and woman, we can try to understand what makes the difference. What is changing one word to become another? And then we can describe this change in a vector. For example, masculinity or, of course, femininity. So if we then look at a vector, we can even apply it to term. So swimming and swam, walking and walked. So we have another vector which is verb tense. And we can then create word algebra because vectors are numbers. And so we have algebra. Algebra is applicable to machine learning. And of course, a vector is an abstraction level because it is giving us not only the number and it is giving us a direction. So we have two dimensions represented in one thing. So we abstract and can simplify in this way. One of the applications for vectorizing is the natural language processing. In this way, this is the model that is behind the text-to-speech logic that we are using every day. And I found that article that was recommended by my colleagues, where you can get more information what is behind an NLP model. So why is NLP useful? We know, for example, that if we look at the sentence, pineapples are spiky and yellow, we can use NLP if we have just the input pineapples are and yellow. NLP will give us the output that is missing, spiky. But we can even turn it around. We can have just one element and then predict the output. And this is what Thomas Nikolov has, together with the colleagues, described in this white paper that I'm indicating here, where you use NLP for describing the distribution and representation of words and phrases. So what we are chasing in cybersecurity is what is making the difference. How can we find out if something has a malicious or a benign intent? If we look at vectorizing, if we look at words, we understand that we see the same behavior, the same structure when we look at API calls. API calls executed by an executional program when it is running. And when we are running such an executable program in a well-observed environment called sandboxing, we can make a list. We can document what it is doing. So we understand the API calls, their sequence, the frequency, the amount of times it is occurring, and the order in which they are executed. And if we then apply an algorithm that is giving us a hint of reducing background noise words, like a, to, what, and, then we understand from all these API calls what is really important here, which are the API calls that are used in this executable file that make a difference. The difference between a benign and a malicious behavior. Another element that is always present in code is sequence. And sequence always has a meaning. It makes a difference what you do first and what you do second. So even this is something that we analyze in our logic when we look at things that could be malicious. And we then change the representation using VGG16 neural networks. So we take the input of raw streams, we break it into vectors, and then we have an abstracted representation of the original data that we can deal with. So what is now the outcome of it? Why is all this useful, or was it just nice theory? We are using these elements, these machine learning techniques, when we analyze executable files in our sandboxing environment. So what you see here, every gray box is a machine learning logic. So first, we do disassembling. We understand the entropy, the structure of the file. We then check which file activities or registry entries are changed. And we look for similarities. And of course, we do verification of all the resources that are accessed outside in the internet. And we create in this phase metadata, abstraction data. And we feed this metadata into a second machine learning logic, which is then giving us a classification if this is benign or malicious. When it comes to Office documents, so PDF, doc, Excel files, PowerPoint, we apply again machine learning logic specialized for this kind of data. And we reuse what we know from the executables. We reuse the logic for URL verification. By the way, this logic is used in many of our solutions, even for a zero phishing solution that we are just now presenting to the market. So machine learning is used in many places, and it's used in two phases. We create metadata, and then we again apply a second machine learning step to the metadata to get the verdict. And what is the advantage? Sometimes we can be fast. Last year, 20th of July, we identified a malicious executable file. We checked on virustotal.com who else has seen this, and the file was in the sandbox environment. Before it could execute its malicious intent, it was blocked by the machine learning logic, and we then allowed it to run, and it was in fact malicious. It was a ransomware. So what we then did is we observed how long would it take for the others to find it. Of course, customers who used the technology that we are producing have been prevented for this technology. And then we shared our finding, and we found that it took others 4 days to understand that this is a malicious file. So sharing experience is a key element. We share our findings with others. It's a public site. You don't need registrations, and you can find tools that you can use in cybersecurity. We publish on a regular basis our findings. For example, when we apply the logic to understand the DNA of a malware. We want to understand the DNA of a malware because it allows us to put it into a family. And we found with all the malware that we have, using a 300,000 dimensional representation model, that there are families, there are commonalities, and if we know the family, then we know which technique we can apply to defend it. And this work was performed even in a specific case with a close collaboration with Intesa, where we mapped out the malware DNA of an advanced persistent attack ecosystem. We wanted to understand what stands behind this ecosystem, and we identified that that ecosystem is state-driven, and that the state is founding multiple teams. Every team is working isolated from each other, trying to achieve the same result. It's an interesting concept of redundancy, because if the work of one team is disclosed and prevented, you have good chances that the other two teams are still successful. So we identified that really the actors didn't share any code. They worked in parallel, and that we found about 60 families in what these teams have been producing. And one of the most dramatic attacks recently has been the sunburst attack that we all know about, where unfortunately a chain of supply software was compromised, and a lot of companies have been victim to this attack. And the attack was utilizing the trust relationship between on-premises Active Directory and cloud-driven directory structures from Azure. And it is unfortunately something that has been observed quite a lot, and where we are very actively monitoring what is happening here to understand and to defend and prevent similar attacks. And one of the most recent that putting down the pipeline in US, and after the team has been paid or actually got money, fortunately the team could be kind of hit back. Some of the money that they received could then be taken away, and the team publicly declared that they are now out of business. Of course, we need to see for how long and how this is going to continue, but this is the unfortunate reality that we are living in. So this is why we put such a great effort in understanding the DNA of a malware, to attribute the family characteristics to it in order to be able to apply the relevant defense techniques. Because then we save our precious element, the resources. So what's next? If we observe the new NLP-trained models, the GPT-3, for example, it has a very impressive set of capabilities compared to everything that was known earlier. If you look at some of the videos, the link that I'm posting here is a video where 14 applications using this machine learning logic are introduced and explained. It's really impressive with how you can just with natural wording create a website, create programs. So recapturing, the machine learning is empowering us to prevent attacks. And it is important to have experience and data. Then you can apply the label. You can select the right features, and then you are able to create the machine learning algorithms that then are available to you to identify unknown malware and to prevent attacks not known before. But this is, of course, not something that we do once and then we relax. We need to apply it every day. We need to apply it in an infinitive circle. We start with a decision point, with federated learning, using data from our customers in an anonymous way so that we do not disclose any customer-related data. We then label. Some of the labeling is supervised by humans. We train the machine. We adjust the weighting. Then we measure the result on unseen data. And then we put it into production, to just then have the circle starting again. A continuous circle of learning, of improving, adjusting weights, and then measuring again every day, from the morning to the evening, and even throughout the night if something bad is happening. So machine learning is nothing without the human experience, and we try to contribute our part to make this a little bit safer, this environment, this planet that we have. And this circle is giving us even motivation. Then whenever we find a new attack, we prevented something that was unseen before, we share it with the rest of the community. We feel a little bit proud on it, and we know that the others will start to tweak their tools to get better again, but we get up again and do our job that we are used to do. I thank you for your attention. I hope it was a little bit entertaining and has given you some new thoughts. Enjoy the rest of the show, Thank you and goodbye.